Okay, so after a long, exhaustive search, we found the working marker. It had hidden itself. So, so we were talking about the 3, 4, 5 and maybe the 4, 5, 6 because you thought that that had a great property that 2 of the sides stayed the same when you increased by 1.
And one side doubled.
And one side doubled. 3 went to 6. So that is a great idea. We knew the area of this. Can you write that in there? The area right in the middle is 6. And we're hoping
The area is 12.
the area of this is 12. But how do we find the area of a 4, 5, 6?
I think since we know the sides, Huron's formula could help us.
Oh, awesome. Okay.
So.
Do you know Huron's? Have you ever heard of Huron's formula?
No.
Okay.
Well, but I think I know another way to do it.
Okay, well, let's let your brother write Huron's formula down.
So
This is a great
the
formula.
Square root of semi-perimeter, which in this case the perimeter is 15. So semi-perimeter would be 7.5.
Okay.
Which I'm just going to write as 15 halves.
All right, cool.
Since decimals and square roots don't usually work out.
Yeah, well, 15 halves. So it's S times,
S minus A.
so we'll call this A.
8 halves, so 7 halves.
All right. So the square root of 15 halves times 7 halves times S minus B.
5 halves.
All right. Times S minus C.
3 halves.
Okay, and so the question is, we want to know, does this very complicated expression, which tells us the area, and which hopefully is on camera. Yep. We're wondering if this is 12. And my question to you is, can you, by looking at this, see if this is 12 or not?
It's not.
Why?
The 7.
What's wrong with the 7?
That the 7, you don't have a second 7.
You don't have a second 7.
And also, this would have to be
These,
144.
you have 2 15s.
You have 2 15s. So that means you can actually tell me the area of this triangle, the 4, 5, 6
So
triangle.
it's 15 times the square root of 7 over 4,
Yeah.
which does not equal 12.
Yeah, well, the square root of 7 is a little bit less than 3. So it's between 2 and 3. So this on the top is between 30 and 45. Let's just call it 40 for fun.
Yeah.
So the area of this is maybe around 10.
So this one doesn't work.
And it didn't quite double. But you know what? That was a great idea. But you also said you had a different idea for the area of this. How would you have found the area?
You could use the Pythagorean theorem and you could chop this in half. So you get some triangles.
But how would you know where it chopped it and what this was?
Well, he wants to chop it in half.
Yeah, but this isn't isosceles.
It's not isosceles.
So
yeah,
this doesn't work.
You chop this side in half and use a perpendicular bisector?
Well, yeah, the problem with the perpendicular bisector is the perpendicular bisector doesn't necessarily go through the point up here because
In fact,
it's not a isosceles triangle. You could use the Pythagorean theorem with what's called an altitude. You have to drop a perpendicular down, and I probably didn't draw that quite right. But then you have the problem of calculating the area of these two side lengths, which won't be the same. But it's not a bad idea, by the way.
So I see. So this isn't an isosceles. So maybe both triangles have to be right triangles for it to work.
Interesting. The question would be, could both triangles even be right triangles? Could you increase the side lengths by 1 and have them be right triangles? Actually, maybe that's a question we actually can figure out the answer to. Do you want to try?
Sure.
All right, let's see.